I uh, I I am having a little surprise technical difficulty here today. I thought I had learned how to do all of this, and is anybody else having? Well, you guys are all here on Zoom, so I guess you're not. I'm getting a request when I log in for a passcode, uh, so that may limit my ability to do this with the iPad again today. Why is it? Do you guys know if there's a how would you guys know the passcode? I guess. Um, I don't even know the passcode. All right, so let me just try uh, to make do without it. I do have the notes here on the computer. Is everybody able to hear me at least? Some thumbs up or something?
Yeah, we can hear you.
Okay, great. All right, so I'm gonna share my screen in the traditional way here. Okay, so these are the notes. There's a packet up that should take us through at least this week and maybe into next week. So this is about counting, which may seem like a completely ridiculous thing to learn as an engineer in college, and yet you'll find lots of situations where the sample spaces are pretty complicated and the kinds of events are complicated, and thinking about all of the conditions that make something belong to an event or not, leads to some astronomical numbers you can't count by exhaustive enumeration. And so we have this whole field of mathematics called combinatorics that deals with counting things according to usually discrete state spaces. So we're usually going to be talking in this chapter about discrete state spaces and cases where all outcomes are equally likely. As we start attaching probability distributions to things, counting isn't enough. You have to think about how much each one weighs. But if 1 and 2 both apply, we have a discrete state space and equally likely outcomes, then the probability of an event A is going to be related to the number of ways that event A can happen divided by the total number of ways that any event can happen in the state space. Okay, so this is a useful sort of universal relation that you see all over the place. So for example, when you talk about entropy and thermodynamics and statistical mechanics, this is really the core of that subject, is counting state space, and you guys won't probably do that in your undergraduate version of that class, but if any of you go on to graduate school, you will definitely see formulas like this related to entropy and probability of microstates. All right, so let's go ahead and talk about some of the actual principles here. Sorry that I don't have the can you guys at least see my mouse, what I'm pointing to?
Yes.
Okay, great. All right, so the multiplication principle is the first thing that we encounter here. If we conduct m sampling experiments such that the kth experiment has n sub k outcomes, then the number of ways that things can turn out is the product of the number of outcomes in each of the k experiments. Okay, so this is, or sorry, not each of the k experiments, each of the m experiments. Okay, so k is the little counter that's telling you where you are in this process. So sometimes I think it's easier to just see these things by example. Lots of fancy words here, pretty simple idea. Okay, suppose you want to choose outfits from a closet, and you have to choose something for the top. You have 3 shirt options. You have to choose something for the bottom. You have 2 pants options. You have to choose something for your feet, and you have 4 pairs of shoes. Okay, so the total number of possible outfits that you can assemble is 3 times 2 times 4, and that's 24 different outfits. We're assuming, of course, when we say this and make any statements about probability, that you don't have any preferences between shirts, pants, or shoes. All right, so that, of course, is often not accurate in real life. Okay, so we have to think about when to use these principles. But if we had believed that all these things were equal, then that would be the number of ways. And if we say, what's the probability that I wear this particular outfit? It's 1 over 24. All right, so let's do another example. Set A has n distinct elements. How many distinct subsets does A have? Okay, so we mean by this, pull them out, decide for every single one, are you a member of the subset or not? It's useful to kind of think about how you would assemble the set in question, sort of to take the question and try to imagine a procedure along with it that would actually conform to the requirements of that set A. Okay, so in this case, we're just counting the subsets of A. And so we have to think about a procedure by which we would obtain them. At least that's the way I like to do these things. And so to count these subsets, we're going to make a whole series of binary decisions. For every single element, we're going to ask, is A1 in the subset? And there are two choices, yes or no. Is A2 in the subset? Two choices, yes or no. And you go down, down, down till you get to A sub n, and two choices again. And so we did this n times, each time accumulating a factor of 2. And the total number of ways that we could assemble subsets then is 2 to the n. Okay, simple idea, but that of course comes up a lot when you think about, information theory and the amount of information that you can store in a given amount of things, right? This is exactly the 0 and 1s of computer science. All right, so let's talk about sampling. I've been using the term already without really saying something about what precisely it means. It's hard to say exactly what sampling means because it depends on the context and it depends on the application and what you're sampling. But in general, it is a process of choosing from a set in some random way. And the nature of the randomness depends on the context of the sampling, the rules and procedures for sampling, the application that you're pursuing, and all those things. Okay, so it's kind of impossible to give a universal description of sampling, and it's really even impossible to give a universal description of random. You will see that we have a lot of different definitions for random, and every time we affix a different distribution to a process or a sample space, then random takes on a different meaning. Okay, but random, I suppose, could in general just mean that the outcome is not predetermined. Okay, so let's go on and talk about some more terminology. If members of a discrete set, you guys should always just stop me. You guys are always on mute, and I just blast ahead because I can't see your confusion. And if you have any questions, by all means, just say pause. I have a question. No questions. Are you sure? I can cover a lot of notes if you guys let me just plow ahead at full speed. So, at UCSB, I found out from my graduate students that some of the graduate students had these planted assigned people who would ask questions to slow me down. You guys might consider a similar strategy, and maybe it would actually be helpful to the whole class to hear the questions and answers, especially if they're legitimate questions and points of confusion. Just a suggestion. Okay. All right. So with no questions, I will go ahead and
chat.
Okay.
Someone
Billy.
in the chat was asking what the backwards E means.
Oh, okay. Okay, great. Good. I apologize. I didn't really cover the notations there. I cannot see the chat while showing this window, it seems. I don't know that that's, oh, here it is. Here it is. I can get it. Great. All right. What is the backwards E? Okay, so let's talk a little bit about some notations that you'll see me use in the notes. A backwards E is like a there exists or there are, and it's just a notation from logic and math that you will find out. Oh, did Zichu send me the passcode? Zichu, is that the passcode?
Yeah, I think so.
Oh, thank you so much. Okay, so you guys are going to see. Zichu is really going above and beyond lately, because I asked her for help with the worksheet today, and she even typed up the Word document. I'm really grateful for that. And then on top of that, she's bailing me out on this passcode problem. Zichu, I'm going to have to remind me to ask you where you got that. All right, I'm logging into the.
It's on the left up top corner
Okay.
of the meeting.
Okay, so right now I'm going to continue ahead like this, but when we switch the exercises, I will switch over to my usual way of all right. All right, so so let me get back to what I was doing here. So so let's go through some more terminology. If all members of I was talking about answering the question about the notation. There's another one that you're going to see, and that's an upside down A. Okay, an upside down A means for all. And then there's this little thing that looks like it's like so you've seen the union and the intersection signs, and if you turn them on their side, they're almost like greater than or equal signs, but they mean contains. Okay, so you know the one. So if I have one of those things that's turned on its side like this, the set over here is contained in the set over here. Okay, and you'll see me use that sometimes. Means that it's a subset of the. It's basically a subset symbol. Are there any other notations that have caught your attention that I use that are strange? No, nothing else. Okay, so backwards E there exists. Upside down A means for all, and I think that I will try to remember to tell you if I use other things. All right, so sometimes when I'm doing a little shorthand, I'll write a little backwards epsilon looking thing, and remind me to stop that. It's such that, but I shouldn't get too carried away with the notations. All right, so so let's talk about two very common sampling procedures. One is sampling with replacement, and that means just what the name implies, that every time you pull out a sample, you record what you got and you put it back. Okay, and that means then that in every sample, you have the possibility of pulling the same element out multiple times. Okay. Then there's also sampling without replacement, which means every time I pull an element out, I record what I got, but I don't put it back into the pool from which I'm going to sample in my subsequent trials. Okay. So that's sampling with replacement and sampling without replacement. The sample that we create can be ordered. That is to say, we care about the sequence in which we pulled things out, or it can be unordered. And that's a common situation where we just care about who comes out of the pool. And in that case, we don't really care the order that we got them. It's just a matter of who ends up on the roster. All right, so so there's a little summary here that I think you guys might find useful. I want you to watch for these patterns in your answers. Okay, so sampling procedures that involve that are done different ways tend to have certain types of calculations that will appear in your answers. And so by your answer, I mean the number of ways that sample can be constructed. And these are the quantities that will appear here. So if you pull out a sample that's ordered, that is, you care about the sequence, and you're replacing items after every time you pull it out, then you're going to get powers. Okay, you're going to get something like an n to the k kind of answer, where every single time you pull out a sample, you get a factor of n, and you do it k times, you're going to get an n to the k in this number of ways quantity. If you create an ordered sample without replacement, then the number of options that you have every time you pull out an item is a little bit smaller than the one before. And that gives rise to this factorial thing, right? So you know that n factorial is n times n minus 1 times n minus 2, etc., all the way down till you get to 1. And so the number of ways that you can do a sampling procedure like this, ordered without replacement, because of the decreasing number of ways as you go on, is going to give rise to these permutations. Okay, so a permutation that involves pulling out k elements from a set of n is going to give you n factorial, but we have to truncate that series of multiplications before we get to 1, because we're only going to pull out k things. So it's n factorial divided by n minus k factorial. You guys probably have seen some of these things in elementary school. I'm aware that today is probably a bit of a review for most people here. And what about an unordered sample without replacement? Well, this one is is, now we're going to have to also divide by k factorial, because once we get our k items, we don't care that we generated them in a particular sequence. We're gonna allow ourselves to permute those. And so permutations have to do with the order, the number of ways you can arrange things in a sequence. And so the k factorial is going to correct for the fact that the particular arrangement that we got was not the only way we could have gotten that set. So we then divide by that to get the number of ways we can get that combination of things in the set. And then there's one here that's kind of complicated, and I will not talk about it probably today at all. And that's an unordered sample with replacement. The plan is to get to this. I know that these have a name, and the book doesn't say what it is, and I couldn't remember what it is. I think it may be called a complexion. Zichu, do you know? Do you happen to know what the name of this thing was? I forgot the name of this, but I will find it, and I will fill in this as we go on in the course. And there's a strange notation here that you may have seen. It's a binomial coefficient, but it's kind of a complicated one, and we will get to this later. Okay. All right. Let's go on and talk about an example where we're using some of these ideas, concrete ways of constructing a sample with each of the three cases that we're going to talk about today. Okay, so these are the ones that we're going to try to get to today: is ordered with replacement, ordered without replacement, and unordered with replacement. Those correspond to cases where you have powers, permutations, and combinations. Okay, so first, ordered with replacement. Okay, so let's take a sample A. That's the numbers 1, 2, and 3. How many ways can we draw two numbers from this set A if the order matters and if repetition is allowed? Okay, so repetition is allowed is the keyword that tells you that I'm doing replacement, right? So I'm not removing that option to see it again, and the order in which I pull them matters. So the set, for example, 1, 2, the sample 1, 2 is going to be different from the sample 2, 1, and so in that case we have the case 1, 1, case 1, 2, 1, 3. We can enumerate these exhaustively: 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. Okay, you can see here just by the way we did it, you've got a 3 by 3, and that gives you 9 different ways. And this was done in the worst possible way that you can imagine. We exhaustively enumerated all of them. Okay, we can do it because it's a small set and we're only pulling out 2 things. But if you get to a situation where you're talking about even like a set on the order of 10 items, and you're pulling out 3 or 4 things, you're going to start to get astronomical numbers that will take you all night long, and you'll probably forget some of them. You never want to rely on the exhaustive enumeration, except for one thing. Exhaustive enumeration is useful for checking your math when you derive a general formula. Okay, this is a very important point. I hope you guys are. I'm deriding exhaustive enumeration as a stupid thing to do. And at the same time, I'm also telling you that it's a really good idea to do it before you just trust the general formula that you derive by using principles of combinatorics. It's easy to make mistakes on these things. And if you derive a general formula for choosing k things out of a sample of n, and the procedure is strange and you have a couple different steps, go back and check when n is small and k is small for a case that you can exhaustively enumerate that the formula that you derive works. It doesn't prove that you have the right answer, but if it works, it's at least far more likely that your general formula is correct. Okay, so how can we get this without enumeration and really arrive at a general expression for this? Well, there are 2 positions in our ordered sample, the first one and the second one. Each one is sampling an experiment in which there's the little there are, so I just lump all that stuff, is a sampling experiment in which there are 3 options at each sample. Okay, so we're doing with replacement because the repetition is allowed, and that means that the number of ways here is to choose 3 and then choose 3 again, and that's going to give you 9. Okay, so again, this point here is important, that as the set that you're talking about grows, this is going to become the gap between exhaustive enumeration and doing things by really thinking about them is going to diverge rapidly. All right, so let's talk about a case where we use permutations. All right, so first of all, these formulas, I mentioned this already, that we will write P sub K superscript N and define that as this, this product, N times N minus 1 times N minus 2, dot, 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 till we get down to N minus K plus 1. Okay, don't forget the little plus 1 here. It's important. You know, we all have to have just a little bit of computer science and programming savvy, I suppose. But if you go to N minus K, you have actually done P sub K plus 1 in. All right, so make sure you remember that little plus 1 at the end. What you're doing is you're dividing n factorial by the ones that you didn't include, right? So n minus K factorial is all the things that came later in the series after you stopped. So n factorial goes all the way to 1 in the numerator, and then you just remove all the ones that you didn't want by dividing by this n minus K factorial. All right, and it corresponds to the first choice. You have n items to choose from. After you've removed 1, because you're not replacing, you have n minus 1 to choose from. After you've removed 2, you have n minus 2 to choose from, etc. All right, so this is your, notice also why you end up with the plus 1. The first choice is here with an n minus 0. The second choice is here with an n minus 1. And you could see that, the third choice with an n minus 2, etc. So you always end up offset by 1 as you go through this series. Okay, combinations. See, we write these in a couple different notations. Your book points out that a lot of people write C sub K n. And then the other way to write this is with the notation of a binomial coefficient. And that is in a little thing that looks almost like a vector with n on top and k on the bottom. Okay, doesn't make any sense if you use this formula. Try not to switch the small number always goes on the bottom, and that corresponds to this calculation. Okay, so it's n factorial. It's the same thing that we had before. Maybe now would be a good time to switch over. It's the same thing that we had before, but we have this extra factor, same thing as the permutation result, except that it has this extra factor of K factorial on the bottom. And remember that the reason that we do that is because we no longer care which one happened first, second, and third. We want to remove that, and therefore we divide by the number of ways to rearrange the sequence in which things were drawn. So these things, these C sub K n's, these are called binomial coefficients. And you might remember from algebra this formula related to raising a plus b to the power n. You get a whole bunch of terms that have a varying progression of things. Anyway, we'll get to it soon. Okay, so it's related to that binomial expansion process. The coefficients that appear in that are these formulas. All right, one last thing to note here before we go on is to note the symmetry. N choose K, I will often just say N choose K, is the same as N choose N minus K. And you can see that symmetry arises from this thing down here in the denominator. Okay, if I switch them, they just, if I put an N minus K here, I would still get exactly the same denominator term out of this expression. Okay, anybody have questions before we get on and do examples of these?
How do you get that, like the whole term from the expression in the parentheses? Is that just like above our level, or?
Oh, okay. No, I think what you're asking is actually another question about notation. So you'll notice here that I have regular equal signs, and I use regular equal signs here and here, and then here I have this little 3-layered equal sign, and it means it's a definition. We are defining this symbol, and we can write it this way. So this is like also a definition. These are just notational definitions, and this, when I see this symbol, it means to do this calculation. So
it's not necessarily like a derivation, it's just like this is fact, basically.
Well, it is kind of a derivation by just thinking about the sampling process and counting. And we're going to do some examples here. The very next examples are going to walk through these two cases and look at you know, I don't know if you can really call it a general derivation, but you can see where they arise by the enumeration process again. Okay.
Okay, thank you.
All right, great. All right, so it's kind of a complicated example, and maybe I should have started with something a little bit simpler. But we're gonna just do this birthday problem, okay? So you have a gathering, with some number of people K, okay? And K should be less than 365. If I ask the question, what's the probability that 2 people share a birthday in a room with 500 people? It's 100%, right? So I will always, if I have more than the number of days in the year, there's no uncertainty about that. It will happen that 2 people will have the same birthday. But the interesting cases, of course, are when K is less than 365. What is the probability that at least 2 people share a birthday? Okay, and we're going to ignore leap year effects. Okay, everybody ignores leap year effects when they present this problem. If you wanted a really complicated problem, that would be one that would be not very interesting, but I don't think it would even have a big effect. Anyway, so we're going to go ahead and just ignore that there are these annoying pesky leap years. Every year has 365 days. All right, so instead of considering the many ways that 2, and 3, etc., so we can think of a lot of cases where people share birthdays. I could have 2 pairs. I could have a single pair. I could have a situation where 3 people have the same birthday. I would have to go through and enumerate all these cases to actually count the ways that 2 people can share a birthday. The easier thing, since I'm told at least 2, is to use the axioms of probability. All these cases add to 1, and I can very easily compute the probability that no one shares a birthday. Okay, and so that's what the strategy is here. The book makes this point nicely, I think. He says that when you see the phrase "at least," you should be thinking about using the axioms, reversing the problem, and calculating the complementary probability. Not always, but sometimes that is the easiest way to do things. Okay, so that's our strategy here, and what we're going to do is to compute the probability instead that no one shares a birthday. So there are no pairs of birthdays in the set. So there's some number of ways that something has to happen that we have to compute, and we want to divide it by the total number of ways that total number of arrangements of birthdays that people could have. All right. So the number of ways that I can have the case that no one shares a birthday, I can think about the process of generating that sample. Okay. I ask the first person, what is your birthday? And there are 365 options. I ask the second person, what's your birthday? There now are only 365 minus 1 valid options because 1 birthday is taken. Okay, I ask the third person, I have 365 minus 2. I keep going, and every time I'm multiplying the number of ways I could have gotten this first choice, second choice, third choice, and I multiply out till I get to 365 minus K minus 1. Notice, Alexandria, that this is 365 minus K. The minus and minus give me the plus 1, and that is exactly the formula that we had here. Okay, so in a sense, it's like a derivation, very specific case, but it's like this is how it arises, right? It's thinking about the process of pulling out that particular sample. And so what I just did here is a bit confusing. I used the permutation P365, PK out of 365 notation. We're also computing probabilities. Please try to remember that when you see this one, it refers to the permutation, and I will also refer to the probabilities with P's. I hope that everybody can stay with me in the context and not get confused by those. Okay, so now we have a denominator term. And so we have our number of ways is just this permutation formula. What if we didn't restrict the set so that people can have any birthday they want and they can overlap with as many other birthdays as they want. Then every single time I ask somebody, what is your birthday? I have 365 options. And so the number of total sets that I can create there is 365 to the power k. Okay, so the probability that no one shares a birthday is P, the permutation of k things from 365 divided by 365 to the power k. Notice that we've already encountered a problem where we needed both things. We had to count one set where we had replacement and one set where we had no replacement. And then we had to blend those two things together to construct the probability in question, because it's a ratio. It's a ratio because of the equally likely outcomes assumption. So we have to count equally likely outcomes that are allowed under this restriction that no one has shared. And we have to count the ones that are allowed when there are no restrictions. And notice this formula is, how do I know that this is always less than 1? Little sanity check here to make sure that we're not writing down ridiculous things. How do I know it's less than 1? Let me give you guys a hint. How many terms were in this numerator thing? Let's count them. I had 1, 2, 3, ... out to k. I had k terms in the numerator. How big are they? Except for one of them, sorry, I've gotten ahead of myself here. Except for one of those terms, they're all smaller than 365. Okay, so I'm multiplying a whole series of fractions. You know, they're always less than or equal to 1. Most of them less than 1, and I'm going to get a result that's less than 1. Okay, so the probability that there is at least one pair that share a birthday now we're flipping this around and saying 1 minus this probability is the probability that I wanted. So the answer, the probability that at least one pair of people share a birthday, is 1 minus p sub k 365 over 365 to the power k. All right. The surprise about this is that it doesn't take very many people before the probability becomes quite small, and that kind of runs against your intuition. I think for most people, we would expect, well, I'm going to need about 150 people before I expect somebody to have the same birthday. It doesn't work that way at all. You don't get nearly halfway. In fact, you only get to 23 before the probability is 50-50. So you have 23 people in one room and ask, you know, what are your birthdays? There's a 50% chance already that 2 of them will share the same birthday. And by the time you get to 57, there's a 99% chance. So almost 100% sure by this point that 2 of them will share the same birthday. And this, I think, in the book explains this really nicely, that this violates your intuition because we kind of get confused over what question is being asked. So the problem that you're computing is that there's at least one pair of birthdays. It doesn't matter who shares them. And the way we think about it is, what would be the probability that somebody would have my birthday? This is a much more specific criteria, and it decays much more slowly. Okay, this one, you know, you allow it to be any pair of people can share a birthday, whatever their birthdays are, and the number of possible ways that can happen is much larger than the number of ways that somebody else in the set can share your birthday. Okay, so this is a you know, common example. It's in almost every book, and you guys have probably seen it before. Thanks for humoring me and letting me go through it anyway. All right, so let's do another example. How many distinct sequences can you make with 3 A's and 5 B's? Okay, and it seems like a reasonably easy question, but we have some complications here. There are some degeneracies. So I'm not going to be able to tell the difference between these 3 A's and which, you know, I also don't know which B is which. So we have 8 positions to fill. How many ways can we choose which ones are going to be A's? Well, that first option is going to be 8 choose 3. Okay, so we make a first choice and a second choice and a third choice, and I have to account for the fact. So I chose, you know, I can think about, you know, I have 8 slots, and I'm going to choose which slot is going to get the first A, which slot's going to get the second A, and which slot's going to get the third A. But now I don't really know which A was which. So I have to divide by the 3, 2, and 1 choices for which A I chose. All right. So now the answer now is 8 factorial over 5 factorial and 3 factorial. It's this 8 choose 3 result. You can numerically calculate that and you get 56. Now, we didn't talk about the B's because once I choose where the A's go, the B's are already set. They go everywhere else. And it would seem perhaps that this problem is flawed because surely I have an issue that I would get a different answer if I had done the B's. This is where the symmetry comes in. If I had chosen where the B's go, I would get 8 choose 5. And remember that 8 choose 5 and 8 choose 3 are the same because 5 and 3 add to 8. Okay, so I would, maybe flip the order in which I write these two things in the denominator, but I would still get 56. All right. So these are cases that really conform exactly to the situations that were designed for using permutations and combinations. But it's useful to not just remember the formulas. You want to try to be able to think about the procedure for generating a sample, think about the rules that sample has to obey, and be able to work with these ideas of replacement and combination and ordering. Sometimes I think it's easier to just start from the beginning. Okay, so here is one last example where we're going to combine the multiplication principle, the permutation ideas, and the ideas of sampling with replacement. Okay, so the permutation ideas are for sampling without replacement, and we also have elements here in this example of sampling with replacement. Okay, so here's the question. How many 8-character passwords can you make according to the following rules? Okay, the rules say, and this is the bane of my life. I don't know about you guys, but every account I have at every institution has their own set of rules for making the passwords. And I would really like to use the same one, a really difficult, strong one that I can just remember. But they're always, somebody makes me change it, and then I have already 2 or 3, and then Bank of America makes you include this special character, and the university makes you include those special characters. And anyway, it's a proliferation, these powers and the number of ways you can generate passwords according to different rules, they grow fast too. All right. So I am perpetually locking myself out. That's the point of this story. And now that I don't go anywhere, I should just keep a list of my passwords here. All right. So enough of my blathering about life's daily headaches. Okay. Each password must have a lowercase letter. Each password must have an uppercase letter, and each password must have a number. No other characters are allowed. Okay, this is a very simple set of rules, and yet you'll see that the number of passwords that can be generated here is enormous. All right, so this is not a standard cookie cutter problem where you can just use the permutation formula, use the combination formula, or use the ordered sample with replacement formula. So what we're going to do is try to think about how we would generate these passwords. First, we're going to choose one lowercase letter and its position. So we have 8 possible places to put it, and we have 26 options for which one we would choose. So we've already accumulated a factor of 26 times 8. Next, we're going to choose one uppercase letter and which place we would put it. So we have 7 places remaining to place that uppercase character, and 26 options for placing it. So we've got another factor in here, 26 times 7. Now we're going to choose one digit and one numerical digit and its position. We have 10 digits to choose from and 6 places left to put it. All right. So we've obeyed the rules now. And now we have complete freedom to pick from any of the digits, uppercase and lowercase letters. So there are 62 possible choices for each of the 5 remaining positions, and the order matters. Okay, so you can see that the remaining options are going to give me 62 to the power 5. Notice how we kind of combined little bits of everything here to construct the number of ways, this thing omega. All right, so now already with this little simple password rule, 8 characters, we have reached a point, there's no way you could enumerate these. There's 2.081 times 10 to the 15 possible passwords that you can create according to these rules. And so, you know, already it's a very long night for the hacker to just discover one of these by random choice. Okay, so as long as you don't you know, use your birthdays and stuff like that, you should be pretty safe. All right, so I think that at this stage we will break and do some. Let's take a 2-minute stretch. I'm going to try to remember to do this during the course. I will often forget your break, but let's take a 3-minute stretch till 11:45. We will reconvene with the first worksheet. Okay, so the one thing you have to do on the break is to load Prairie Learn and log into Prairie Learn and be ready to start that worksheet in 3 minutes. All right. You guys, I guess, so you guys could open this. All right, I'm gonna go ahead and redo my sharing here. And I shared the whiteboard, but I'm gonna remove that. Stop sharing. All right, let me just collect my thoughts here. What do I need to do? Where is my Zoom? All right, so here we go. Share screen. This is the one I want to share. All right, so this is the Word version of the Prairie Learn exercise that you guys are working. Okay, so you have this necklace, and there are beads, and every bead is a different color. Okay, and they're in beads, and the question is, how many different necklaces can you make? All right, so this, you know, might seem like an easy problem, but actually there are some tricky aspects of this thing. So let's go ahead and hopefully everybody can remember this little image. I will go ahead and draw some versions of this as I work on the whiteboard. But this is the question: how many different necklaces can we make from this bead? So, you know, the assumption here is that there's no knot, no obstruction to going all the way around this circle. That's an important thing that I maybe should have stated in the problem statement. All right. So let me go ahead and stop sharing this. And I'm going to share my whiteboard here. All right, so this is the problem. We have our necklace, and it has these colored beads. And the first thing that I'm going to do is just consider the case where obviously if there's one bead, we have one necklace, okay? But let's consider the first case where there's actually some counting to be done. So this is one possible case right here. And what I want you to try to think about is, you know, so this is one necklace, and you might think, well, I can also flip the order of the red and the blue beads, but I can also just flip the necklace upside down, okay? So if I just turn the necklace, if I imagine just taking the necklace and flipping it like this, then that blue bead will be sitting over here, and the red bead will be sitting over here. And I effectively already have a count, you know, my one arrangement of the beads when I put them on is both of these two necklaces, okay? So the case where there are two beads just becomes one way, okay? All right, so this is the case where n was equal to 2, and there's just one way. So we are doing this, you know, it might seem at the beginning by exhaustive enumeration, but we're doing that for a reason, because as you go, you know, this is not a, you know, just straight pull the formula out of the book. You have to really think about what are the rules, you know, what makes two necklaces different, and what are all the ways I can tinker with them and try and rearrange the sequence that I first envisioned. All right, so let's see what happens when we have 3. Okay, so n equals 3. We've got a necklace with 3 beads. Can you guys see the yellow? Hopefully you guys can still see the yellow. All right, so I've got my necklace with 3 beads, and I can flip it. Oh, well, is there an undo button? Yes. All right. If I flip it, I get this one. And this is an important thing. There's now, when we have three beads, we see the appearance of a new operation, right? So these are like operations that create degeneracies. So this sequence and this sequence are not different because of a flip. Okay, imagine just taking the whole necklace and flipping it upside down. But also, I have a degeneracy that comes from the fact that I could take this red bead and bring it all the way around the necklace, and I would get this sequence. So doing this, I'll call this a cycle, and this one is a flip. Okay, let me erase my picture of this. You guys saw what I did. So if I did that, then the red bead would rotate to be over here. The yellow bead now is in the middle, and the blue bead is on the right. All right, so and you know what you can see here is that now if I flip these, I get you know, two more, and I can cycle through and put the blue one on the other side. I can get blue, red, yellow, and I can flip those. Okay, so your naive you know, first instinct answer would be there are three things, and I want to consider all the permutations. That's going to be 3 factorial, right? But in fact, you can see here that through flips and cycles, I can generate every one of these necklaces. So this case n equals 3 still has just one way. All right, so what's going on here? What we're going to have to do is to now begin to think, and it's going to start to be difficult to draw these pictures, but now we can have some intuition for the way that this works. I can do these cycles until I have let everybody be the leftmost bead, right? So I can say, you know, start with an arrangement. I can bring the yellow one around, and I can also bring the blue one around. And so already 3 factorial has become 2 factorial. I removed the factor of 3 because of the cycling process, anybody can rotate around to become the first bead. Okay. And the flips take every sequence that I generate by these cycles, and there's a reverse one that is exactly the same because I can flip the necklace upside down. So that I'm also going to remove a factor of 2. And so you see that when I started with that 3 factorial, I removed the factor of 3 because there were 3 beads that I could cycle through. And I removed the factor of 2 because of the flip. And I got left only a factor of 1. And so, you know, we seem to understand now how this process works and how I can evaluate the number of necklaces for any given case. Okay, so let's see if we can write down a general formula. So, you know, I don't want to write down a specific one, right? So this is just this arbitrary case n is going to give me, let's see if we can write it down. So we have omega is going to be the number of ways that I could, you know, my naive thinking is just how many ways can I permute those n beads if they were on a line. And then I have to divide by the degeneracies created by the flipping operation and by the cycling operation. So that is divide by a factor of n and divide by a factor of 2, right? So this comes from the cycles, and this comes from the flips, and this comes from the, I will write, naive permutations. All right, so that turns out to be the right answer. You can check that. Oh, I'm sorry. I should put a special requirement in here. Okay, so check your formula and make sure that it works. So we already saw that it works for case n equals 3, and if we were really diligent, we could check it for case n equals 4, and it works again. So this is gonna be valid for the cases n greater than 2. Okay, what about the case where n was equal to 2? Well, notice now I have 2 factorial divided by 2 and a factor of 2. There's a problem. It doesn't work for the case when n is equal to 2. Why not? Who can tell me what's wrong with my logic when I have the case n equals 2?
There's no cycle.
Yeah, in a sense, there's no cycle, or you could say that a cycle and a flip do the same thing. When there's, I don't know which is really the right way to look at that, but it's clear that the cycle and the flip just count for the same exact degeneracy, right? So that's a special thing that happens when n is equal to 2. And so we need a different formula for the case n equals 2. Both, either the flip or the cycle, it doesn't matter which one we call it. They're both a factor of 2. But the point is, oh, I don't have my nice my nice thing here that allows me to go farther down the whiteboard. So it's equal to this for that case, and it's equal to n factorial. Okay. I didn't want to work on two screens here, but let me show you how you would write this with proper notation. So we would say that omega is equal to n factorial over 2n for the cases where n is greater than 2, and omega is equal to, I could write it out, I could write n factorial over 2 for the case where n is equal to 2. I could also just write 1, right? This is kind of a complicated way to write 1. And I can get away with just doing this. There's only one necklace when n is equal to 2. For all cases beyond that, this cycle and flip consideration works, and we get this formula. Okay, so this is hopefully this helps. You guys will see a lot of these kinds of notations in the class, and sometimes I forget to explain them so that everybody's on the same page. All right, so I think that you guys now have everything you need to go through and enter your answers into the Prairie Learn worksheet. Out of curiosity, while you guys are doing that, let's think. Actually, I'm not sure what the question really asks. Zichu, should I do some of these special cases where we consider numbers of beads? I think I should. Just let me know if I miss anything that they're supposed to enter. Okay. All right. So we're gonna check this for the case n equals 3. Okay. Oh, sorry, we already did that. Okay, one way. The formula reduces to one way. Okay. What if we did it with n equals 7? All right. So n equals 7. We're starting to get a sizable necklace here. How big does this end up being? Well, let's apply. We're clearly in this case. Okay, for n equals 7, we're going to use this formula. And so omega is going to be equal to 7 factorial divided by 2 times 7. And that's equal to 6 factorial divided by 2. And that is going to be 300. So if you want to remember how this works, that 6 factorial is 6 times 5 times 4 times 3 times 2, but the 2 is going to cancel. Okay, and we're left with 360 necklaces that we can make that are unique. I can't convert one into the other once I've put them on the loop. All right. What about the case where we go to, let's say, 31 beads? I mean, you guys probably already have an intuition that would say, don't even try to count them. It's astronomical number. Okay, so let's go ahead and do it though. So we get that omega is equal to 31 factorial over 31 times 2, which ends up being 10 to the 33. There, obviously that's an approximate number, but it's approximately 10 to the 33. Okay, so that is really inconceivably large. It's billions of moles, and so let's learn a little bit of a useful approximation for working with these giant factorials. I should stop and let you guys put in the Prairie Learn answers. I should also take questions. Does anybody have any questions about what we've done so far? Okay. Hopefully everybody's entered the Prairie Learn exercises. I want to show you something that you might encounter along the way. It's you know, this is the kind of thing that if I ask you to use on an exam or on a quiz, I will give you the formula. But I just want to show you that it exists so that everybody is aware of it. It's extremely useful little result called Stirling's approximation. And that says that, you know, eventually you get to a point where even computing these quantities in factorial, you know, if I put in something like 10 to the 23 in here, if I'm doing statistical mechanics, this can actually happen. And if I want to compute the 10 to the 23 factorial, that number is just, you know, even the calculator will explode. There's no way to even conceive of how big that is. But you will find that many times we want to take the logarithm of n factorial, where n is something enormous. And there's a very useful way of doing that. Use this asymptotic approximation called Stirling's approximation. Okay, so Stirling's approximation says that n factorial grows approximately as n to the n, e to the minus n times the square root of 2 pi n. Okay, and to think about how this is useful, well, it immediately allows you to get a very good order of magnitude estimate. In fact, as n gets larger, this approximation gets better. So it gives you a quick and immediate order of magnitude estimate that I can just use the rules of logarithms and write this quantity here as 10 to the power n log of n over e plus the log of the square root. These are log base 10s, 2 pi n. Okay, so we're writing it in base 10 here. So these logarithms are base 10, just to make sure there's no ambiguity here about what I'm doing. All right, so you can see here that I can very quickly, and in fact, probably this is already how you're getting the result before. So we did this case where we wanted to plug in, compute the 30 factorial is already an enormous number, and this expression then is going to give you a very quick way of saying what is the magnitude of 30 factorial. Well, I just write it like this: evaluate these things, which are easy calculations to do. These are easy to do. Okay, and then none of those numbers are particularly large. It's the raising them to the power of 10 that makes the number enormous, and you can get that order of magnitude then quite easily. Okay, so how does Stirling's approximation behave? Well, if I make a little table here of n versus the percent error, this is the real answer minus the Stirling's approximation answer. So this is taking, in this table we have the real answer minus the Stirling's approximation answer divided by the real answer. Here is your percent error. And when n is equal to 1, it's not very good. It makes the 7.8% error. Okay, so you don't use this for very small numbers. But already when you get to n equals 5, then you have only a 1.7% error. And, that's starting to become okay for most purposes. Easy enough to compute 5 factorial, and you don't really need it yet. But by the time you get to 10, you have a 0.8% error. Stirling's approximation is looking pretty good as an alternative to multiplying 10 by 9 by 8 by 7 by 6 by 5. It starts to get difficult to key all of that in, and you have this other way of doing it. So, of course, what's really nice about Stirling's approximation and what allows us to call this a true asymptotic approximation is that in the limit, as n goes to infinity, the percent error goes to 0%. Okay, it converges asymptotically, we say. All right, so so I think that that's it for this example. Let me go ahead and see if we can have time to work this other example here. So this is a another little silly example here with we have Coach yells a lot, okay, and Coach yells a lot has a team that he's going to assemble from 12 players, but he has some restrictions. Okay, so players A and B won't play together, and he has to make a starting lineup of 5 players. Okay, so there are 12 players. He needs a starting lineup of 5 players, and he has a restriction that A and B won't play together. All right. How many possible starting lineups can he make? And so we have to think a little bit about a little bit about whether it matters. You know, there are 2 possible ways we can think about this question. One is like a basketball team where you have I don't know much about basketball, but you have a point guard and a forward and a center, and there are 5 positions basically, and it matters who goes into which one. So this would be a case where the sequence matters. You are putting them into specific slots. So in that case, we're gonna make a little tree diagram. Sometimes a useful way to think about this. We start at the beginning. We haven't made any choices yet. Okay, so I put a little vertex here to indicate that so far there's just one way accumulated, and that one way represents we're going to make a team. Okay, the first choice that he has to make. Okay, so we're doing this case where positions matter. Okay. All right, the first case, he's going to choose to put A on the team. Okay, and he can do that in 5 different ways. Okay, so there are 5 ways to do that because A can play any one of five positions. All right, and now we have the number of ways to put the rest of the players is to permute 4 from the remaining 10. Why are there 10? Because I put A on the team and now B can't be on the starting lineup, right? So that's one branch of my tree. Another branch of my tree is that I put B on the team. Okay, and again, there are 5 ways to do it, and it results in this number of choices for the rest of the players. Okay, another way I can do it is to put neither of these 2 difficult people on the team. All right, and now I leave open, how many options do I have left open now to place the remaining players on the team?
Permute 10 and 5.
Good, 10 and 5. Okay, so there's still 10 options to choose from, but I haven't selected A or B, so now there are 5 of those to permute. Okay, so now what do we do with these things? Do we multiply them together? Do we add them? What do you think we do here?
Wouldn't you add them?
I add them, right? So it's really important. You want to develop an intuition. When do I multiply and when do I add? So I split this into mutually exclusive sets and I counted each one. And what I want to do is count all the ways. So I'm going to count each of the 3 mutually exclusive cases. Neither A or B on the team, B on the team, A on the team. There are 3 different branches. I add them all together. Okay, so the number of ways total is going to be 5 times P for 10. That's the first branch, plus the second branch is 5 times P for 10. And the third branch is P 5, 10. Can you guys see that? I got pretty close to the edge there. Somebody confirm you can still see. I right off the edge of the screen.
We can-
All right. Okay, good. So so this is the number of ways, and I did not do the actual calculation to see how big that number is. Somebody maybe can tell me how many there are there. Anybody want to tell me how large that number is? Nope, no answers. Okay. Let's try and do another case where the positions don't matter. Okay. So, for example, in volleyball, all of these players are rotating through, occupying every position on the court over the course of a game. And it doesn't really matter now who plays what position. And so all I'm concerned with are the number of ways to pick the five team members. Thank you so much, but I have 5 minutes left and then I'll be done. Okay. All right. So so let's do this case now where we have where the positions don't matter. Okay. For example, volleyball. Okay. Now you guys tell me. So I'm going to make the same tree, but the choices are going to be a little bit different now. So how many ways can I choose to put A on the team?
Would it just be one way?
It's just one. I make the choice. He's on the team or he's not. And so there's one possible way there. And how many different teams can I make given that I chose A to be on the team?
Would it be 10?
So there are, I still have the restriction that you're right. There's 10 to choose from, but I'm going to pick 4 of them.
All
What
right.
is that number?
4.
It's 10 choose 4.
No.
It's actually an enormous number, right? So it's a number that's probably on the order of 1,000. So you can see that it's already growing pretty large again. Okay. I have another option is that I can put B on the team. That's just a factor of 1 again. And how many ways are there to choose the remaining players?
That would be 10 choose 4 again.
10 choose 4 again. Okay. And the third option, neither A or B is on the team. All right. And how many ways are left to choose the remaining players?
10 choose 5.
Yeah.
10 choose 5. Excellent. All right. So, and what do I do now? Add. Great. Okay. So I add these up and I get 10 choose 4 twice. And I get 10 choose 5 once. And that's the new number of ways. So, choosing a basketball team is different from choosing a volleyball team. It's in one case, I only have to think about who is on the court. And in the other case, I have to think about who's going to play where. Okay. And you can see that these numbers, if you evaluate this number will be enormously smaller than the one that we calculated for the case where the sequence matters. Okay. Because it has all of these denominator terms that weren't in the other part. And we didn't have to choose these factors of 5 of where to put the initial A and B players. Okay. So hopefully you guys are a little more versed in how to work these problems. There are lots of examples in the book that are worked There's one cute problem in there that I really love is this question of, if you take, it's called the rencontre problem, and it's quite famous because the answer again ends up being really counterintuitive. So I think in the book he explains it in terms of people come to a party and they check in their hats, and then when they leave the party, the hats are distributed back to random people. Just everybody gets a random hat. What's the probability that at least one person gets their hat back? And your intuition would say that the bigger the party, the more likely my hat goes to someone else, and that's certainly true. But also, there's a growing number of people who could get their own hat back, and the two factors kind of in the infinite limit, they go to 1/e, which is really quite a counterintuitive result. I mean, there's so many aspects of that I think are fascinating. Why does this transcendental number pop up out of a problem that involves purely discrete counting? And so these things are pretty fascinating. If you love the mathematics behind this stuff, it can be pretty fun. Anyway, let's go ahead and adjourn there. Make sure that you enter your answers in the Prairie Learn worksheet, and that's it for today. Thank you, Zichu, for all the help.